All set? All right. Welcome back from lunch, everyone. My name is John Luginsland, and today it's my pleasure to be talking to you about the plasma and electro-energetics portfolio. Just to reiterate, we've had a small change in schedule. We're going to go right through the talks with no break, and they told me I can take up to 3 hours on my talk, so that's what I'm going to do here. So, first of all, I'd like to just thank Dr. Jason Marshall. I've actually been on a detail with Dr. Christian Schopp for the past month, and Jason's been doing a great job leading reviews, handling the PIs and all that, so thank you for that, sir. I appreciate it. There was a question as to who should speak today, so we played a vicious game of rock, paper, scissors, and here I am. So, in following the outline, I decided this time to talk a little bit about the history of plasma physics and what makes plasma physics interesting. This morning you've heard a lot of plasma physics. It's popped up in several portfolios, and I think that's reflected by the graph on this, which shows the temperature versus density phase space of the plasma universe. And you'll see that there's plasmas all over the place. There's plasmas in stars, there's plasmas on Earth, and all sorts of interesting and different sorts of things you can do with plasmas. It also has a long history. These charts have to start out with us going back to as far back as we can. So Hercules, it's Greek. I'm not sure if he's Trojan, Howie. Might be Spartan. But in keeping with that, you can see that there's lots of glowing, beaming light, things like that. And in general, that's where people got the hook. Why are these things glowing? Okay, and you can see as we went through up until the 1940s when we actually had Alfvén doing cosmology. So what's interesting about this and what differentiates it from the plasma physics you see in the other portfolios, we're trying to look at the fundamental processes underlying plasma physics and be able to hand those over to the specific applications that might exist in other portfolios. So I like to say this is a 7-dimensional problem. You worry about position, 3 dimensions of position. You worry about how fast it's moving, 3 dimensions of velocity. You also have to worry about time. So it's nonlinear, it's electrostatic and electrodynamic. In fact, formally, if you're into that sort of thing, this is how you close Maxwell's equations, is with plasma physics. You worry about statistical mechanics, relativity, quantum mechanics. It's a hard problem, and that's why we have it both in several portfolios as well in the fundamental plasma physics portfolio. So spend a little bit of time on what makes a plasma interesting. What's the plasma fundamentals? At the end of the day, a plasma is an energy-dense object. I take a solid and I stick energy into it, I get a liquid, I break the bonds in the solid. Stick energy into it again, and I get a gas. Stick energy into it again, and something interesting happens. I rip the electrons off of the neutral atom. So now I have positive charge, ions, and electrons flying around in a bath. That's what we call a plasma. When that happens, they tend to glow and give off light, so suddenly photons pop into the problem. And in particular, so it's an energy-dense object, but also because it's positive and negative, it's got long-range electrostatic and electromagnetic forces flying around in it. In particular, if I stick an object into a plasma, as shown in the yellow dot, here charged negative, the plasma will react to that and attempt to shield that out. We're going to call that Debye shielding, and that's a fundamental plasma process. It's on page 2 of almost every plasma textbook, and I hope to show you that it's still interesting and dynamic today. There are several new results on that fundamental question of the plasma shielding out applied voltages. Similarly, if it is in a magnetic field, the electron, say, or the ion in a magnetic field will rotate counterclockwise to generate its own magnetic field. It is attempting to reverse that plasma that's being applied to it. It's diamagnetic is the term. And so it resists both electric fields and magnetic fields and attempts to keep those fields at bay. So we have long-range forces, which introduce the complicated physics, but we also have this fact that the plasma is pretty much an ornery cuss and doesn't let you do what you want to do to it, kind of like me. So you see another instance of the plasma phase space, and there's lots of interesting phenomenon, lightning, magnetic fusion, inertial confinement fusion, the sun. Some of that's been touched on in the earlier portfolios. I do both laboratory plasma physics and also natural plasma physics, but with definitely a strong emphasis on laboratory plasma physics. So again, to summarize, these plasmas are energy-dense objects, and they resist applied electromagnetic fields because of their self fields, and we need to deal with all of that. Oops. Second part of my portfolio is electro-energetic physics. This is simply the idea that if we want to get into the plasma state, we need energy to do that. One of the best ways to do that is electrical energy. So I can't, unfortunately, since we're in the Air Force, I can't stick a power cable onto my airplane and fly around with that. So we look at ways to package that power and then deliver it in such a way that we can make plasmas. And we're back to the same question. We're packaging energy. Now we're packaging it in solid state materials. And, for example, capacitors. You see the plot. The plot shows the energy density versus the power density, so there are lines of constant discharge time on that line. And one of the things you see as you increase the rate at which you pull power out of something, the amount of energy I can store in an object goes down. Okay? That's an actual engineering result that's well known, but no one really understands why. No one understands what the limits are to beat that. So we have a fundamental question here of what is the way that energy and charge transport through these objects. Sounds a little bit like plasma physics, right? We've got a dense object, we've got charge and energy transporting through it, but now we're talking about solids. And so there's a lot of work on linking this energy storage to the actual plasma physics and what sort of things result when you couple those two together. So those are the two fundamental areas in my portfolio. So what are the challenges? We need to understand, manage, and engineer this energy density. We need to stick it where we want to stick it, such that the materials survive long enough to do useful work. It's inherently multi-scale and multi-physics. We need to do solid-state physics. We need to do plasma physics. We need to do quantum mechanics, all of that sort of thing. You'll get a flavor for all that. But I'd like to summarize that all in the sense that we're looking at how energy flows from point A to point B. In other contexts, we call that thermodynamics. And that's really what we're doing here. What's the thermodynamics of these energy-dense objects? So, my bang box. Why is this different from other people? High energy density plus multi-scale means non-equilibrium. By non-equilibrium, in fact, my colleague Dr. Schlossberg always says, everything's non-equilibrium. Luginsland, what are you talking about? In this case, it means there's lots of pathways for this energy to go. That results in the plasma being hard to control, and that's the physics that we're really looking at. How do we get to do useful work with it? And again, non-equilibrium, your mother told you to avoid nonlinear, multivariate, time-dependent problems. I just didn't listen. To give you an idea of what I mean, and it is energy density, the island figure is 2 nuclear reactors being built currently in China. I stole it from Wikipedia. 2 times 700 megawatts continuous power coming from those things, and they fit on an island. We're trying to do the same thing in something roughly a meter cubed, like the magnetron shown there. Gigawatt class power levels, it's exactly like the magnetron that's in your oven, it just does billion watts. Can make popcorn at 2.5 miles. And again, energy density is the question, and what's the physics that results from that? Now, it's an eye chart here on the Air Force opportunities. You can look at that. I'm happy to talk with you offline on all those sorts of things. But in particular, what I'd like to just touch on is directed energy, which is shown either in the CHAMP source or the active denial source. We take pulse power and we use that to generate very high electromagnetic fields to do interesting military things, radar, communications, directed energy munitions. In the middle chart, you can also see here, we can make plasmas and break them down for counter purposes. That is to say, if I have a big field and it goes out into the air, we actually make a plasma. And so that's a fundamental limit to the directed energy technology. It's something we look at in our portfolio. Another thing that we do, however, is non-equilibrium plasma physics, which is shown here. That's actually a combustor system for a hypersonic engine. Think of it as a really fancy spark plug. And the short pulses and intense pulses actually lead you to different chemical reactions than you can get to from a normal spark plug. So the fuel burns more completely. We have higher energy efficiency, things of that nature. We try and understand that. And finally, although we don't do a lot in this portfolio anymore, there's interesting things where you apply plasmas to airframes, to air bodies, airfoils, and lo and behold, small amounts of energy have a big difference. It changes the dynamic. You can see the transition from turbulent to laminar flow with a small introduction of energy in that. We try and understand those sorts of questions by the addition of plasma, all to help the Air Force. So again, often far from equilibrium, and in the interest of time, I'm just going to push through this quickly. It's energy-dense objects. Energy-dense objects could be high-powered microwave devices like the planar magnetron, shown up there from the University of Michigan and also Kirtland Air Force Base. It could be plasmas in the ionosphere, which is work done by the Air Force Research Lab at RY with the Naval Research Lab. Also could be the pulse power and the fundamental transport of energy and charge through solid objects, and we cover a whole range of timescales. So that's the playground. My investment strategy is I'm a huge believer in tightly coupling experiment, theory, and simulation together. I think that they all need to work together. We need to understand if there's a difference between experiment and theory, why. It works in a leapfrog manner, and we try and improve both the theory and the experiments and the diagnostics as we do that. So I fund experiments, fund high-performance computing, hardware and software, applied math and theory, as well as diagnostics and pulse power. I also am a big believer in teaming across AFOSR, especially today in the physics department. You saw a lot of instances where it touches on plasma physics. Try and work with my colleagues there. I also reach out across the departments. I, in particular, am thinking of with Dr. Ali Sayer, who works on materials far from equilibrium in the solid state and is a natural ally in what I'm trying to do. And also we team across the government. You can see the laundry list of people we work with. Okay. The sub-areas that I'm going to talk about today include relativistic high-powered electromagnetics, which is also called sometimes high-powered microwaves. Microwaves is, of course, a technical term. I tend to mean it in the sense of lots of high-powered electromagnetics, whatever the frequency is. So sometimes we'll call it high-powered electromagnetics. We'll talk about non-equilibrium plasmas, where the plasma, either the species are not in equilibrium, or there's chemical energy in the system that's not in equilibrium, or it's not in equilibrium with the electrode that's being stuck into the plasma. And then finally, pulse power is an area that is the fundamental underpinning that drives this. And we have a new interesting area where we've pulled some thermal science into this, in particular the physics of phonons and electron coupling, and try and look at this. And this is really a new start for this subthrust in trying to get at what are the fundamental limitations of pulse power as opposed to just looking at another interesting electrical engineering configuration. And you see the relative distribution. It's pretty even across all those. So, I'm just reminding myself, I promised I wouldn't walk around, so if I start to look like I'm... Today, first thing I'm going to talk about is the subthrust of high-powered microwaves, also known as directed energy, also known as relativistic high-powered electromagnetics. What differentiates this from the other parts of the portfolio is they tend to be single species, the plasma is non-neutral. Think of an electron beam accelerated to relativistic energies. And unlike an accelerator where you keep pushing that to higher and higher energy, we take that energy that's stored there and pull it out coherently so that we get tremendous electromagnetic fields out of it, gigawatt class. Okay? Pat Roach introduced the relativistic magnetron with the bumpy cathode. And in particular, what we're going to talk about here is new results relating to how do we get electrons from the pulse power through the cathode and into the device. So all of these things start without a plasma there. So we need to figure out how to get the plasma into the problem. And in this case, we actually put on little tiny pointy lightning rods. We apply voltage to that, and those lightning rods explode, and literally we quantum mechanically tunnel electrons out of that material. Here's an example of a test cathode jig, which is four rods made of carbon nanotubes that are then wound into fibers and cut. They're 10 microns in diameter, 2 millimeters long. And there's a bunch of questions about this. This material, because it's quantum mechanically emitting, we worry about what's the work function of the material? What's the barrier between the material and vacuum for electrons getting out? Okay, that's one feature. The second feature that we worry about with these is what's the field enhancement? If I apply a voltage on this, and this is a pointy object, it's a lightning rod, what is the modification of the field from that then allows the electrons to tunnel out? And the third thing that we're adding here is these are all conductors, so the fact that they're next to one another affects those fields. So there's a field for a single fiber, there's a field with fibers together, and then there's the fundamental material properties of this, okay? That, amazingly enough, and the phenomenon we're talking about here is called Fowler-Nordheim emission. It's been known since 1911. Amazingly enough, those three things have not been teased apart in the 100+ years that we've been working this problem. So this effort actually looks at very careful experiments with simple fibers and looking at the emission. And one thing you'll see as you add fibers, it takes more and more voltage to get current, okay? The fibers are identical, and they go through a rigorous process to ensure that they're identical in the spirit of their barriers being the same. So we make sure they're the same materials and they have the same material barrier. We work very hard to make them as identical as we can so they have the same field enhancement, and then we do 1 fiber, 2 fibers, 4 fibers. I'm reminded of the story of the physicist who worked on the stability of a table, okay? If it had an infinite number of legs, it was stable. If it had 1 leg, it was unstable, and he spent the rest of his career working on the 2-leg problem, never solved it. So with this type of situation, what we're finally doing is isolating the quantum mechanics from the classical problem at the end of the day. Okay. Why do you want to do that? Because our codes that do this, and this is a picture from IcePick, which is, as Dr. Roach mentioned, one of AFOSR's truly great success stories. It's a virtual prototyping capability. It's been funded for over 20 years continuously, and it is outstanding. If you want to do a microwave device, it is by far the best particle and cell code in the world. Out of all the codes the DoD uses, it is the 2nd highest code in terms of hours burned on DoD supercomputers, and it is the only code in the DoD high-performance computing arena that was home-written. The rest are all from outside. So it's an outstanding AFOSR achievement. But it's basically a classical code. So we're trying to figure out what's quantum, what's classical, so that we can put the right algorithms in that code. Okay. Let's say we do that successfully, and now we're going to apply voltage, and we're going to rip electrons out of that and all that sort of stuff. You get what you see here. Now, those are those cathodes emitting, and there's no magnetic field, so you see the spraying out that's going on. Okay. That spraying out is called, in the technical term, admittance. It's a phase space volume. It also just means the beam's getting wide. Okay. That wideness means that we've got velocity in the direction we want to go, axially, but we also have sideways dimensions. If I apply a magnetic field to that, that shows up as velocity spread. So this admittance turns into how messy your beam is in phase space. One of the things we'd like to do is to go from high-powered oscillators to high-powered amplifiers, to move from a directed energy munition scenario to being able to do radar and communications. And that admittance spread is what kills you for doing high-powered radar. Okay? It's a fundamental problem. And the question is, we don't quite understand, again, the electrons start off in the material and get ripped out. Is there any influence of the electrons in the material that persists into the vacuum? Okay. The new result this year, and it's a joint team of AFRL and NRL, and you know, it's a real tragedy when the Navy has someone that's really good.
Who is that?
That's Kevin Jensen. Yeah. But you know, we're interested in getting smart people. We heard that earlier. So we'll even work with the Navy piece in our time. So the question is, there's several different types of ways to get electrons into the vacuum. I've told you about this tunneling process. We call that field emission. Second option for doing that is you whack it with a laser, which is the laser comes in, hits the solid material, couples to some of those electrons in it, and pushes it over the barrier, hot electrons. Okay? Tunneling is one process. Going over the barrier is a second process. The third process that I'll talk about today is thermionic. You just make the cathode, and this is a technical term, stinky hot, and lo and behold, the electrons literally bubble out of the material. You have to have the right material to do this, but it is a way to do that. So the interesting question here is, how much do those electrons remember when they get pulled into that material? What you see here are 3 plots, thermo, photo, and field. Okay, and what you see, amazingly enough, and if you look in particular at the dashed lines, you see the admittance is different between those problems. The hot electrons that are associated with the thermionic in the field retain that heat and actually set the initial conditions which set the admittance. So that's a problem for us building an amplifier at high power levels. Field emission, or so-called cold cathodes, don't have that problem. Now, what's interesting about this calculation is it's a mixed classical quantum calculation that does an exact treatment of the electron supply function within the limits that this is a perfect metal. That's, in fact, the next step that we're doing. But it also captures the fact that it's on a perturbed tip. Normally, those types of calculations are done in one dimension. Okay, so we're actually capturing classical geometry, quantum mechanical supply function, and this is all getting rolled up to actually figure out what are the fundamental limits for doing high-powered amplifiers. And indeed, Kirtland is getting ready, because of this work, to do an experiment on both measuring this inherent emittance spread, which will be the first of its time, and then seeing on what the limits are and what we can do to actually modify that to control things. One last little plug down in the lower corner. We made the cover of the Journal of Material Research. This is our newest STAR team. This is folks at RD and at RX, and they actually are building out of nanotubes, they're building now paper, and paper that can actually literally be cut with scissors and shaped into whatever type of field emitter you want. They're macroscopic paper sheets and being tested right now as we speak. So, great work. You could do origami on it. So, once you have that beam, you want to have it interact with a structure such that you produce intense microwaves. This is a Muri with Dr. Nachman. And in particular, there's two things that we want to work on here. First of all, metamaterials are very common. They're way cool, but you see, if you put high power on them, they smoke. So the question is, what do you do in the geometry to fix that? And then what other things can you do to make a high-powered amplifier? So the first thing you can do is, this is actually a copper so-called split ring, which is a typical metamaterial, on a dielectric, and it's actually the dielectric, not the metal, that's failing. So you can actually do a complementary split ring where you actually have metal that you punch out those dimensions. Okay? This is a proposal from the University of Texas. Our Muri team took that, and you see how this looks the same no matter how I look at it? The insight of Dr. Nachman's theorists was that metamaterials have very much tried to be isotropic. If you're willing to be anisotropic, that there's a preferred direction where you want your metamaterials, it gives you a lot more design flexibility. So you can see this is now a split ring that has been stretched in this direction and compressed in that direction, then we have two slots. Okay? That lets you get both bandwidth, which is something metamaterials don't tend to do, but the bandwidth is only in the direction of propagation. And then you fire your electron beam down that structure. It interacts with the electron beam, with the electromagnetic modes, excuse me, and you see we get bunching on there. So this is actually being built as we speak. It's RJ's theorists working with my experimentalists, and if you thought the Navy Air Force peace in our time thing was good, theorists and experimentalists working together, true peace in our time. I don't believe it. Switching gears, now we're going to talk about non-equilibrium plasmas. And as I mentioned before, what do I mean by non-equilibrium? Almost everything is non-equilibrium. In this particular case, what I'm interested in is what happens when I have a dense plasma where there's a lot of potential energy. Okay. This is actually sonoluminescence. So I fire in ultrasound and I actually cause a bubble. It's a liquid, sulfuric acid, and I squeeze it down to micron size. It's a new effort. And as that happens, I squeeze the bubble so hard it actually goes into the plasma state. It's beyond solid density when that happens. It is a very strange plasma. What I was showing you earlier is its gases that you ionize. Now this is a 10 to the 21, 10 to the 22, 10 to the 23, 10 to the 24 density plasma in the plasma state, transiently. Okay? Now you can see actually what happens is that it bounces there and then recovers. This is actually measured using me scattering. That's the laser light you see. So you can get you know how much energy you're sticking in? It's a very clean experiment. But what's interesting about this here is that we're getting way more plasma light than we should. Now I could go on about transparency and opacity and all that kind of stuff, and I'm happy to talk about that offline, but the gist of it is that because of the density, the collective behavior associated with this, even the process, and by the way, everyone knew this was non-equilibrium, But what's different about this is the density is actually modifying the ionization potential. We tend to think of that as something fixed. I have an atom, I have an electron, I pull that off, that takes a certain amount of energy. At high density, such as they're doing here, two things happen. One, you get shielding from the other electrons that are around that you're ripping off. That's that Debye shielding I mentioned in the fundamental section. Okay. People didn't really expect that to happen here. The other thing is that because you have atoms that are close, even the bound electrons are changing the plasma orbit and changing what it takes to pull those electrons off. It's called hybridization. So shielding and hybridization result in the fact that the ionization potential drops by a factor of 80%. Okay. This is just put out in physical review letters and has caused lots of interest across the community, not only in the DoD, where this affects questions of modeling fireballs and modeling engines and things like that, where the ionization in very dense situations pops up, but it also is important for our DOE friends because they've been worried about their constitutive relations in their codes. And this is a clean way to get at fundamental transport and material properties. So before you worry about whether your code is right, what's nice about this is very simple analysis, reproducible and clean, using theory actually from Zeldovich, the Russians, that is immediately able to be used to modify our most advanced supercomputer codes. And again, it's a change of what we used to think of as a fundamental constant of nature. Second thing on the strongly coupled section, I briefed this last time. This is a BRI with Dr. Tatiana Kurchik. It's another teaming effort. It's experimentalists from the atomic and molecular community coupled with the plasma theorists. And strongly coupled plasma is a situation which doesn't happen in your plasma textbooks. It occurs when you have a very cold plasma where the kinetic energy is low compared to the potential energy. Plasmas are normally the other way. They're hot, right? We think of the sun being this way. The way you get here is you cool something using the techniques that Dr. Kurchik mentioned earlier, and then you hit it very precisely with a laser that 100% ionizes it, but imparts almost no energy. You're just breaking the bonds, okay? So these are plasmas, say they're calcium atoms that are ionized. They're 100% ionized, maybe 2 million, down at millikelvin temperatures, and yet they're fully ionized. That is a weird beast in the technical lingo. That is measured by something called gamma, which is the top is the potential energy versus the kinetic energy or the temperature, okay? The struggle with this is, and by the way, this seems esoteric. Why do I care about this? Oops. I think, did I just unplug? No?
No, you just need to say, you know, we all that.
All right. All right, still hear me? Okay. Why do I care? Right, thank you. These strongly coupled plasmas occur in all kinds of Air Force scenarios, like fireballs, and in spacecraft in the ionosphere. The spacecraft and the dust in the ionosphere fall into this category, and they modify the interactions. So the situations that where this work will be used are in other people's portfolios. But this is a fundamental plasma physics question. How do you deal with this plasma where the potential energy is bigger than the kinetic energy? Okay. In particular, I talked earlier about this shielding. That shielding should happen here too. But I'm really cold, so I can't move very fast to do the shielding. So how do I add the effect of shielding? That's sort of a standard term, that lambda is the Debye shielding. That's a conjecture there. But the gist of this is that we do these things. We've got a million calcium atoms. We ionize them, and they heat very slowly. And we pull out what the effect of the strongly coupled is on the equilibration process. Now when I do that, if I have extra electrons in this strongly coupled scenario, what you see is that I get gamma significantly above 1. This is in the ballpark of where our ionospheric plasmas are. It can be that high, okay? What you can see is that the model is actually capturing this until you get to a kappa, which is the Wigner-Seitz distance divided by the Debye shielding, or whether the Debye shielding is shielding out the whole distance between atoms, you can see that the model works pretty well and then starts to diverge. These are molecular dynamics calculations that have been modified to do particle and cell along the lines of what Dr. Para talked about. So this is a fundamental question of how things equilibrate. And what I love about this kicked off the timeline was 7 months. The two authors on this, Mike Murillo and Scott Bergeson, met at the kickoff meeting. They had a paper 7 months later. 7 months after that, it's already been cited 7 times, so it's great. Okay. Switching gears one last time, and on to pulse power and new efforts that we're doing in pulse power science. The question here is how much energy you can store. And we've been looking at nonlinear materials. This is STAR team work out of Kirtland by Susan Heiger. And if I plot the electric field versus the displacement field, which includes the dielectric constant, for a linear material you get an object like that. For a paraelectric you get that. For a ferroelectric you get that. Different materials have different amount of energy storage capability versus the loss that's associated with it. We usually build our capacitors out of this, but you see there's a lot more area. And so we're actually trying to take advantage of those types of situations, okay? We're doing that with ab initio quantum calculations. I talked about this last year. You'd think things like what happens on the ends, the layer on the end, really couldn't matter that much, but of course it's how it attaches to the electrode, and it's critical. That work's continuing, but the really interesting thing is, after I've done this work, which I briefed last year, I'm happy to talk about it offline, this is what a real material looks like. It's a lump of goo. Okay, so how do I actually start taking what I've learned from the 6.1 and apply it to real manufacturing processes? I still think it's a fundamental question, because I need to do quantum mechanical calculations to understand how to do this. And with the high performance computing assets in the STAR team, they're actually building now larger calculations that capture material that they actually take samples, they actually scan that in, so this is actually a computational excursion around that, and then do calculations on that. That work has just started. But this illustrates my investment strategy of forcing theory and experiment to work very closely together. That's how you get leapfrogging, that's how you get really good results. It's the ability to run down the hall and say, what did you mean by this? So that's leading to new types of pulse power. The thing I'm excited about adding this year is more fundamental looks at how energy and charge are actually transported in this system. This is Pat Hopkins' work. He's my YIP from the University of Virginia. One of the things that's great about AFOSR, actually, Rick Para introduced us. So what he does is he does pump probe with femtosecond class lasers and wax material. The first material, whacking is a technical term. You hit it with thermal energy, and then after a pump probe, after a delay, you probe it and see where that energy has gone. It's specifically used to isolate what happens in interfaces. So a couple quick things to learn about is, it's probably hard to read that, but there's many orders of magnitude going on, and this one diagnostic can actually pick out the electron-electron coupling, the electron-phonon coupling, the so-called picosecond acoustic status, which is when our normal sonic equations don't work. It's an intermediate regime. And then finally we go into classical heat transfer and acoustics of that sort of stuff. And with this type of technology, you can actually look at the hot electrons I was mentioning earlier, the electrons that are whacking the phonons, that energy coupling, and how that energy then goes through materials. They've had several publications on metal silicon interfaces to sort of prove the technique, and now they're going into doing pulse power type situations and watching where charge goes, especially where the capacitor comes in contact with the electrode. And that works with Dr. Sayer. So I hope I've made the case that I like collaborating. I talk to everyone. There's a laundry list of MURIs and BRIs that I do with other people. And you can kind of see where that is in the distribution. I believe Dr. Stargell, I was listening yesterday, briefly mentioned the computational mafia, where there's several of us that are interested in advanced computation. Just one thing from the co-design BRI, AFOSR was one of several agencies that funded the University of Tennessee's Beacon supercomputer, which was #1 on the green supercomputer, or flops per watt. So if you want to stick a supercomputer in your home, these are your guys. And it lasted a grand total of maybe 3 weeks before they got knocked off. But interesting sorts of things where what they're doing there is varying the precision as you do the calculation with getting the accuracy you need. Of course, that assumes you know what accuracy you need versus the amount of energy you're using. And that allows for a type of supercomputer that you could imagine actually could be put into the field. Imagine you have SAR radar in the field and you want to look at it in the field, or you even want to put the supercomputer on the UAV. This is the sort of enabling technology that lets that happen. And so I'm very proud of the plasma physics organization, or my portfolio, but more importantly of AFOSR and the breadth of plasma physics that we do. It's a great place to be. So I'll just end with, we do femtoseconds to hours, nanometers to kilometers, solid state to plasma to warm dense matter. It's great. I really do believe we are the leading DoD agency for directed energy technology in the 6-1 arena, and I'm proud of that. I'll be happy to take any questions. Sir.
I was wondering if you could go into any more detail on what you might be doing in plasma-assisted combustion.
Sure. So there's some efforts in my portfolio which is on, first of all, in particular, I am looking at the pulsed power that drives those types of situations. So that's transient plasma ignition is the particular area that I do, so nanosecond class pulse power. Then we have people that look at diagnostics for that scenario. So what happens, the plasma is ignited in a nanosecond, it quenches in 100 nanoseconds. The combustion event starts in microseconds to milliseconds. So what's different? How are we getting benefit from that? And so that's sort of the area of fast plasma diagnostics and pulse power. My colleague Chip-Ing Lee, however, who is the combustion portfolio and I believe is talking on Friday, also has a strong plasma combustion portfolio. And he is looking at, I would say, an allied feature, which is how do you modify the combustion tools to include the plasma effects, so GRI, MEC, and kinetic sorts of things. Related to this, there is a new BRI just starting this year with Dr. Mike Berman, which is plasma chemistry, which we are actually looking at questions, allied questions of fuel reforming and things like that. So what does the plasma let you, how does the plasma let you get to different chemical pathways, I think is the question.
Just a comment, I think it's probably appropriate to acknowledge Bob Barker, who unfortunately lost him over this last year.
Yeah. So Dr. Barker funded me in graduate school and passed away this past year. We are going to have a ceremony for him at the ICOPS, which is in DC in June, and if anyone wants to come, we'll work that out. And Bob's a great guy. I miss him a lot. So thank you, Gernot. Other questions? All right.
Okay.